Hello everybody and welcome. Today we will be introducing something called centripetal force. Ever thought why rotating objects never flies away from its place? Well, obviously the string is keeping it from doing that. And previously we introduced that any force inside a string or a cable or a chain, etc., it's called tension force. And tension force is equal to the force applied on it. So what is the force that is applied on this cable or this rope or this string, etc., that is causing this tension? Actually, it is the centripetal force. So the force called centripetal force exists because of uniform circular motion. The centripetal force is always directed towards the center of the circle. So this force can be found using this very simple equation. We can say that centripetal force is equal to mv squared over r. Actually, it is very much related to Newton's second law. Actually, it is Newton's second law because we know that force is equal to the mass multiplied by acceleration. But because this is a uniform circular motion, I can say that it's mass multiplied by acceleration, and we've introduced before that acceleration is equal to v tangent squared over r. So it's just the same equation. It is Newton's second law. So actually there's nothing new here to know, just that this force is caused by the centripetal acceleration and it's always directed towards the center of the circle. Okay, so it's very easy and straightforward. Another very famous example is when a car is moving in a circular path, it is also affected by centripetal force. But what's holding it in place? Actually, the answer here is friction. The friction between the wheels and the floor is opposing the centripetal force that cancel each other. Therefore, the car stays in place. That's why it's very much recommended that we change our tires every now and then, because if this friction force is not there anymore, this will cause the car to lose its control when it's in circular motion, because the friction won't be able to cancel the centripetal force. Okay, now let's solve some problems. Question number 1, it says that a toy car of mass 0.1 kilogram travels in a horizontal circular path around a track of radius 0.5 meters at a constant speed of 5 meters per second. The magnitude of the centripetal force that the rock exerts on the force is, so it's asking me to simplify Fc, or the centripetal force. It's equal to mv squared, or tangential squared, over the radius r. So we can say that it's equal to the mass 0.1 multiplied by the tangential velocity, which is 5 squared, which is 25, divided by 0.5. So the answer in this case is going to be equal to 5 newtons. Okay, so it's very easy. Next question. A small ball is attached to a string and is swung around a horizontal circular path with constant speed as shown from the top view. Okay, so we have a circular motion. If the string were to break when the ball is at point P, so here's point P, if the string were to break, the string here, imagine that now it's broken, in which direction would the object fly? Actually, you can see from the arrows here that it's going in this direction, so it's going this way. Okay, now we can say that the tangential velocity, it's in this direction right here, vt, and here we have fc and dnc. Actually, they don't represent anything. Now, which lettered arrow would show the direction of the motion of the ball immediately after the string breaks? Well, actually, the object will go with direction B. Why is that? Because it's in the direction of the velocity, and the object always goes in the direction of the velocity, so the answer is B. Next question. Question 3 and 4 are related. A 2 multiplied by 10 to the power 3 kilogram truck travels a constant speed of 12 meters per second around a circular curve of radius 30 meters. So I have here Vt, okay, and I have here the radius r. Okay, what is the magnitude of the centripetal acceleration? AC is equal to Vt squared over r, so it's equal to 12 squared over 30, which is equal to 144 divided by 30. So the answer, it's clearly equal to 4.8 meters per second square. Now, as the truck goes around the curve, the centripetal force is directed towards the center of the circular curve, away from the center, tangent to the curve, tangent to the curve, opposite to the direction of motion. Well, actually, the centripetal force is always going towards the center of the circular curve, so the answer is A. Next question, questions 5 and 6 are related. A ball is attached to the end of a thin rod of negligible mass. The other end of the rod is attached to a frictionless pivot, and the rod spins freely in a circular vertical plane. Oh, so there's something new here. We're talking about a vertical plane. In other words, it's not going horizontally, it's going vertically. So it's going up and down. So if we're going to draw this man, he's trying to swing it, the object is swinging this way. Okay, so it's not swinging horizontally, it's not going this way, it's going vertically, it's going this way. Okay, so in other words, gravity is within the equation. So gravity, or the forces caused by gravity, is within the equation. Now the magnitude and the direction of the ball's velocity at 4 points of motion are shown. Okay, so it's clear that this is the velocity of the ball at certain or different points. When the ball is at point P, the direction of the acceleration is most nearly choice A, choice B, choice C, or choice D. Well, actually, if the ball is at location P, okay, we know that the direction of the acceleration will be this way, AC. So which is the closest answer? I think the closest answer will be. Now question 6. The tension in the rod is greatest when the ball is at the top of the circle, greatest when the ball is at the bottom of the circle, or when it is at point P, when the point is directed opposite to point P. Now actually, let's study the cases A and B, when it's at the top and when it's at the bottom. Okay, so let's start when it's at the top. Now we know that this is the string holding it. We know that we have a centripetal force that's going downwards, Fc, and this is causing a tension inside the cable that's going upwards. So the tension inside the cable is going this way. It's trying to fly upwards, so the tension in the cable is this way. Now, we know that also the weight will start affecting this object. So the weight is going downwards because the weight always goes downwards, which is mg, for example. So here, tension and mg are opposite to each other. So let's see the other case when the object is right here. Well, I know that the centripetal force is pulling this way because it's always pulling toward the center, which is causing a tension in the cable in the other direction. So the tension is going downwards, and actually the weight is also going downwards because the weight always goes downwards. So the maximum tension in the cable will be at this point because both the centripetal force, or the tension caused by the centripetal force, and the weight are both going downwards. So we can say that the answer here is B, the greatest when the ball is at the bottom of the circle. Stay tuned. In the next videos we will be introducing something called the gravitational force. See you then.